acceleration, and I'm clearly not accelerating right now. So I'll have, as a physics teacher, I think my job is to ponder that, but not right now.
Okay.
So how much time is this thing?
Oh, I just started it over because it
Okay,
stopped.
it stops after 30 minutes. Gotta hurry. Sorry. All right, this alien craft business, I think I'll just tell you the answer that as the alien craft falls, the moon pulls it downward and the spaceship pulls the moon upward. Which one gets pulled more?
The spaceship.
The spaceship, because it has less inertia and it's going to move less with that same force. And you won't even notice the moon moving, but it will. Okay, the 2 kilogram ball, it's thrown directly upward, and it's in the air for 3 seconds, which really doesn't matter, but I'm just going to write, I'm going to show the velocity of it. 30 meters per second, 20 meters per second, 10 meters per second. What is it at the top? 0. And then it comes back down, and now it's negative 10, now it's negative 20, now it's negative 30. What was the acceleration at the top? Negative 10. If you made a graph of its velocity, you would have velocity at 30, then 20, then 10, then 0, then negative 10. So it would be accelerating at negative 10 meters per second the whole way. And I think when I wrote this down, I think I wrote 10 instead of negative 10. Yep, there it is. Sorry about that. The third question, what's the net force on the ball when it's up there? Anybody get that? How many newtons of force would there be on the ball? There's only one force acting on it. What is the force? Gravity. And gravity gives you weight, which is mass times g, or you could say force equals ma. So the force acting on the ball is the mass of the ball times the acceleration, which is 10, so you get 20 newtons. Really, I should have said negative 20 newtons because this acceleration should have been negative 10, but not a big deal. Number 21, heavy things like this. This is pulled to the earth with a greater force than a lighter object. Say, oh, I don't know. I wish I had a little weight here, because if I compare it to this isn't as dense. But if I had a piece of lead, and I had this rock, and I dropped them, and there was no air resistance, they'd fall at the same speed. This one is being pulled a lot harder than the lighter one. Why doesn't it go faster if it's being pulled harder?
And the same acceleration.
They do have the same acceleration, but the question is why? If this one has more force on it, why doesn't it accelerate faster? Sheldon. More inertia. So the same force is going to, or a greater force is required to accelerate this at the same speed because it has more inertia. So just the quick answer to this is heavy things have more inertia, which prevents them from speeding up more quickly. Even though they have more weight pulling them down, they're not going to speed up faster because they have more inertia.
Wait, so they have more inertia, which causes them to what?
They have more inertia, which prevents that greater force from making them go faster. Like it's a self-limiting kind of thing. Yeah, your greater mass means you're going to have more weight, but to counteract that, your greater mass also means you're harder to speed up, so it doesn't really make you go fast. Now there's the late question. The other classes I kind of thought that everybody had discussed this weird physics conundrum at some point, but maybe clearly I'm just a physicsy nerd, so that's why I had heard about this. You have a perfectly frictionless lake, and you're stuck out in the middle of it, and you have a bowling ball, and you have a feather. There's a feather. So what do you do to get off the lake? Laura?
Would you push the bowling ball in the opposite direction that you want to go?
Exactly. Let's say, well, I know you're closer to that side with the bowling ball sitting here, so you just push the bowling ball this way. That's going to be the action. What's the reaction going to be?
You go the
You
other
go
way.
the-
Bowling ball pushes you that way. Now, why would you use the bowling ball, not the feather?
Car doesn't have
Has-
much inertia.
Feather has less inertia, so when you try to push against the feather, you can't really even apply much of a force to the feather because it doesn't have much inertia. It would work. You could take a feather and throw it really hard. It just wouldn't push you back very much. The feather would go really fast. You'd go really slowly. Now, if you had like I happen to have here, if you had a nice, need somebody?
Just looking.
If you had a nice wall sticking up in the middle of the lake, you could just take the wall and throw it like I've been throwing the wall, and that would work. Now the first question though is use Newton's third law to explain why this is a problem. Why can't you just walk to the edge of the lake?
You don't have any friction to like under your
If you
feet.
walk, you
Under
just-
your feet. Yeah.
Why do you need friction under your feet?
To like hold the ground like when you walk.
Yeah, when you walk, you're actually, well, if you dig in with your claw-like toes, then maybe you pull the ground. Most people,
Well,
I know what you mean. I'm being silly. When you walk, you push off usually, or you can pull if you have claws. Dig along. But
I had some
if I try this, if I put my foot down and I push that way, I go this way. If I tried that and I was on a frictionless lake, what would happen?
You would just slide.
I would go like that. And somebody said last class, why don't you just get the ball, the bowling ball, and go like this? So that was a good idea. Well, what would happen if you went?
You would eat straight in your face.
So what would happen is when you push the ball that way, which way would your body go? This way. And when it got to the end of your arm, it would pull you back the other way. So you can kind of go. But you can't really get beyond
How does the
that. If you go, then you go back and the ball goes away. Yeah.
is it when you bowl and you like spin the ball like on TV with like professionals? Is it because the like whatever?
Because you spin it.
Yeah, no, when you spin it, but it doesn't spin till like the very end, and then it.
Right.
There's
Why
no
does it catch
friction
it?
on
Is
the-
it-
I don't know. Is it because of the way they wax the lanes?
Yeah.
So they wax them until the end, and then it just bites in and turns. I don't know. I've always
No,
wondered that
because
myself.
right when it comes out of your hand, it's spinning much faster than it is when it's been rolling forward.
So is it just?
it's not.
It finally catches up with itself.
So it finally.
So it slows
So you're
down
saying the
enough to
spinning
actually
slows
turn the
enough
ball.
that it can finally catch?
Yeah.
Yeah.
Yeah, that's what I used to think, but it could be the waxing too. I don't know.
Isn't it like as like the round goes on or whatever? Like,
Whole lane is waxed.
Well, that's
yeah.
look that up and tell me. I don't know. Let me uncover my answers now. So for A, to use Newton's third law to explain why you can't just walk to the shore. Normally you push back on the floor and the floor pushes you forward. On the frictionless lake, you can't push backwards. Somebody in another class said, use the bowling ball to make a crack in the lake and then grab the crack and push yourself. That would work if you could do it.
That's pretty.
B, which is more useful, is the bowling ball because it has more inertia. C, how could you use the bowling ball? You push the ball away from shore and the ball will push you toward shore. Now, this section, I apologize for this. This was so screwed up. I'll definitely make sure it's less screwy on the actual test. I might divide this into a few multiple choice questions, but at any rate, here are the answers. Number 23 was acceleration. There were two accelerations. They were H and K, either one's okay. And that just says when a force is applied, it's inversely proportional to the object's mass. So the acceleration of this is inversely proportional to the mass. The more massive this is, the less it accelerates. If I have something less massive, it's going to accelerate more. Inversely just means opposite. Acceleration and mass are opposites. Mass goes down, you accelerate more. Mass goes up, you accelerate less. I think I should make that a standalone question. 24, M, this torque. Torque tells you how much force it takes to rotate an object or to stop an object from rotating, and the formula for torque is that. You just need to know, if you're talking about twisting something or rotating something, really torque is the term we should be talking about. And I haven't really taught you enough about it to apply formulas, so I want you to be familiar with the term. 25, friction, F is resistance to change in motion. 26, no.
Wait,
Friction, inertia, F is inertia. Sorry about that.
is that an I? 26?
That's an L. 26 is L, which would be work.
Though.
Work is a force applied over a distance.
Oh, yeah.
27, directly proportional to the object's acceleration, that's force. Now I would take either A or G I realized there was force and there was net force, and I should have just had force up there. Either one is okay there. And directly proportional means if the force goes up, the acceleration, it accelerates more. If you put less force on something, it accelerates less. That's kind of obvious. 27, friction, D, always opposes motion. 29, that's L, work. Work is the equivalent to the energy you put into winding your car. 30, this is acceleration. It's either K or H, a measure of how fast velocity is changing. 31, J, terminal velocity. That's the point when your weight equals your air resistance. 32, D is friction. That's caused by the bumps and surfaces. 33, B, that's a vector. A vector quantity has magnitude and direction. 34, force of gravity is E, weight. 35, C is a scalar. Scalar has magnitude but not direction. And 36, that's A, which is a force, push or pull. You could also have G there. Moving on, blanks on the table. The first left side of this table, this was stuff we've done before. Meters per second squared, seconds. The right side gets a little tricky. Mass is kilograms. Everything else is newtons. These are all forces of some sort. A force is a force. Weight's force of gravity, so that's newtons. Friction is a force. Those are all newtons. Now, I like these questions. You notice that the font changes, and that kind of identifies when I'm using somebody else's questions. These were some that were on the common assessment. And I like these. They're kind of tricky, but I think they're kind of fun too. But then again, I'm a physics teacher. I'm going to write the 3 formulas that you need up here. I've written these before and I just erased them. There's net force equals ma, and there's A equals net force over m, and there's m equals net force over a. What I do is just try to complete. I like to try to get the net force if I can, and if I can't, I just figure out where else I need to go. I don't know of some method that's always going to work with these. You just look at them and see what you have and see what you can figure out. So you've got a 2 kilogram block in this. There's no acceleration. If there's no acceleration, what's the net force? 0. And if the net force is 0, and you've got a 30 Newton force to the left, then you also have to have a 30 Newton force to the right. So that's it. This one, I like the ones where I see 2 opposing forces, because from that I can get the net force. 40 newtons to the right, 20 newtons to the left. The net force is going to be 20 newtons to the right. And at this point, all I'm looking for is acceleration, so I go to my acceleration formula for this one. And I just plug in the net force divided by the mass. This should be a 20, half of the 0 I'm going to erase. 20 newtons divided by 10 gives me 2 meters per second squared. On this one, again, it's kind of nice. There are 2 separate forces, so I can get a net force. This is 20 to the left, 15 to the right, 5 newtons to the left. The tricky thing is when I start to use my formula for mass, when you use the mass formula, I've got to remember that a force to the left is what? Negative. So that 5 newtons, when I put it in numerically, it's got to be negative 5 newtons divided by negative 5 meters per second squared. I get 1 kilogram. This is it looks like all the same stuff you had in the last question. 10 minus 2 is 8, so there's a net force of 8 newtons to the right. And you can use mass equals force over acceleration to get the mass. The net force is 8, and the acceleration is 8, so again it's 1 kilogram.
Is that 200 N for the 300 N? Or
Over here,
yeah, is that 200?
that's a 200 that's written there. But keep in mind for all of these, the F in these formulas, that's the net force. don't use one of these, because this mass isn't really being accelerated by a 15 Newton force. It's being accelerated by the net effect of those two forces, which is that. So this one over here, this is probably the most involved on the page. You've got to do a couple of things. You can't just jump right in and use a formula for acceleration, because you can't know the net force right off because you don't have both of these forces. So the first thing you have to do is figure out the weight of the thing. And at the beginning of the test, there's the formula for weight. I don't really even like to bother with it myself. Weight equals mg, because it's really just the same thing as that. Weight is the force of gravity, m is mass, g is the acceleration of gravity. But it's there for you if you need it. So no matter which one I use, I still take the mass of this thing, multiply it by the acceleration of gravity, which is 10, and I get 100 newtons. So that's the weight. There's a 300 Newton upward force. So the net force is going to be 200 upward. And now I can figure out the acceleration using this formula. Acceleration is the net force divided by the mass. We're not going to have the test over this until next Thursday. I know there's some things that your mind needs time to digest, and you're going to just get sick of it if you study this all at once. So I want to give you plenty of time. If we have to do it after next Thursday, that's okay with me too. This next one gets a lot easier, just the way things turn out. The first thing to do is to figure out the weight. The weight, the mass times gravity, 60 times 10 is 600. And that's nice because the weight equals the upward force. If this is a falling object, this is a special moment for it. What do I mean? What am I getting at?
Terminal.
It's that terminal velocity. It's when its weight is equal to the upward force, so it's not accelerating anymore. It's either hovering in space somehow, or it's falling at a constant rate. Yeah. Now the bicyclist is moving at a constant velocity. I like this question. If the bicyclist is moving at a constant velocity, what is the bicyclist's acceleration? Zero. So what's the net force acting on the bicyclist?
0.
0. So the acceleration is 0, the net force is 0. If the motion isn't changing, both of those are 0. Now the next question you have to is more of a real question. How much force does the bicyclist have to provide to keep moving with a constant velocity? She's experiencing 200 newtons of air resistance.
200 newtons.
So she needs to provide how much?
200.
200 newtons, yeah. So if air is pushing her back with 200 newtons, she has to push forward with 200 newtons to balance that out. 39. 39. These next few are just plug and chug kind of problems. You can just be half awake and go through the problem and then look, oh, what is acceleration? I just need this acceleration formula. So I'm going to start looking for a force to plug in and a mass to plug in. And you don't have to think any more deeply than that. So the force in this case is a 40 Newton force, and it's pushing a box with that mass. 40 divided by 10 is 4 meters per second squared. The next one, you have to think a little bit. The next one asks, if you had the same situation, but now there's 20 newtons of friction, what's the new acceleration of the box? So I'm just drawing the picture. I've got a 40 Newton force forward. Friction is always going to be opposite that. So the net force is 40 minus 20, which is 20. And now I can use my formula for acceleration. Acceleration is that net force divided by the mass, so it's 2. So it's only going to go half as fast as it did when there was no friction. Friction took away half the force. 41. Does anybody know the answer to 41? What's the weight of a 9.8 Newton object?
0.98.
What'd you get, Malin? Approximately 1 kilogram, 0.98 kilograms. But to get this, you you're using the mass formula, net force over acceleration, you need to know if you're talking about weight, what acceleration is causing your weight? Gravity. So that's the acceleration you plug in there.
Wouldn't it be negative?
Yes. Well, this would be negative, and that would be negative, so this would be
Oh,
positive.
okay.
You'd have a 9.8 Newton force downward, and you would have 10 meters per second squared downward, so you'd have a positive mass. No antimatter in this question. And the last one, the slingshot. The slingshot apparently takes very large rocks. My answer was 450 kilograms. I didn't make up this question. Somebody else's question. So the mass, you're trying to find out what mass should you use if you have a slingshot with this much force and that much acceleration. So 450 kilograms. And now for the last one. How's the time doing on that thing?
You have 9 minutes left.
Okay,
How many classes do you have to do this for?
2 more.
You could just play your movie.
Sucks.
I could, but I'm not gonna do that.
Let's do it next class.
The last one?
Let's have a Halloween party next class.
Except
Halloween
we
was
already
3 days
had
ago.
Halloween, so.
Someone else like Halloween.
Well, we should do something fun.
Too bad.
I'm planning on, because some of these problems, people are having such a hard time visualizing them. I think it would be good to do some stuff to help visualize them as fun. So we'll be doing some fun labs the next couple of classes, I think. I'll bring in my hovercraft. We can ride on the hovercraft. It's just a small hovercraft. Don't get too
Does it
excited.
actually have a trap?
Yeah, hovercraft. It only hovers this far above the ground, but there's no friction. It's like riding an air hockey puck.
Can you actually ride
which is
around on
kinda
it?
cool.
You should hear
What?
You can actually ride around
Yeah.
on it?
Yeah, I could put you in the hallway and give you a push and you just
Oh,
go.
can you bring it?
Yes.
What?
You're gonna bring it.
You have a hovercraft?
What's
Which
the-
will be so much
Yeah,
better.
we
to
would
do.
charge for
What
rides.
is the weight limit on it? Can you put an actual person on it?
I've had somebody, I won't name names because this person was here at the tech center for a while. He was a very large boy. I think he was 250 pounds.
Was his
He
name,
rode it.
Oh,
is it like a Mexican sounding
No.
name? Oh.
Yeah. Why don't you stop that and we'll just do a new one.
Mexican.
No, I wanna watch that.
Oh, wait.